Now that I've given you a ugly uh, circuit to work with, let's look at circuits a little bit different. We're going to look at them in terms of conservation laws. And the two rules that you'll hear mentioned are the loop rule, loop, not lur, should be a P, and the junction rule. These are Kirchoffs laws. And all this says is that whatever current I have coming out is going to be the same current coming back in. So I've labeled this I1. I1's coming back in this way. So I1 is coming out that way. And it also says that I'm going to use up all of my potential as I go around my circuit. So the nice thing about this conservation law is that, well, that means that if I draw a loop in here, and I'm just going to go in the same direction as these arrows, that means I'm starting with 5 volts here. I'm going to lose some of it going across this 3 ohm resistor, and the rest of it coming over this 5 ohm resistor prior to coming back here. So all of my voltage will be consumed. The current in is going to be equal to the current out. That is a loop rule. It's saying I'm losing all of my voltage. A junction rule is what we were talking about in analyzing the circuits last week. It says that I'm going to have current coming this way, and I've labeled this I1, that it has a choice. It can go this away, I2, or it can go this away. And what have I labeled that? I've labeled that I3. So if it has a choice, then I am going to get some of it going both directions. That is a junction rule. So let's see how that looks. For my loop rule, I can start off with my 5 volts. So I'm going to call this, now I'll just leave it as 5 volts. So my 5 volts Actually, I'm going to back up a little bit. Instead of writing an equation, I want to point out something important that is going to save you dividends in time later. And that is labeling your high and low potentials. So coming out of a battery, I always know that I have a positive, so I'm going from a high potential to a low potential. And I've defined the current as coming out of the high and coming back into the low. So that means I am losing voltage here. So I'm going from high to low across that resistor. And this is the same direction that I've defined the current. So I'm going from high to low here, and then back to whence I came. And the reason why that's important is you'll see that the current coming out of this one, this would be my high and this would be my low, is going to be in the same direction, just if by defining it as going from high to low, but that's not always going to be the case. So keeping track of what direction you originally define high to low is important, because this is one of those things you cannot change midstream. So it's kind of like when we define our axes, you can't like change the direction, the designation of positive and negative on your axes once you get going, because once you've used that designation, it'll mess up your math later on. So same thing here. Okay, so I have my 5 volts, and conservation says that I'm going to lose, let's call this V2 and V3, and this I'm going to call V battery 1. So 5 volts, I'm going to lose V2, and then I'm coming around this corner. This is how I've defined my loop, and going around V3, so I'm going to lose voltage there too. And now I'm coming back to where I came. That means that in the end, that whole thing equals 0. So another way to write that is that my 5 volts is going to equal volt 2 plus volt 3. Now remember, we've defined voltage in terms of current and resistance as being V equals IR. So I can rewrite this in terms of the current and the resistance. So my 5 volts equals, let's see, what have I labeled this? I've labeled this 1. So remember, I comes out and the exact same amount of current comes back in. So I have I1 coming out, going across, let's label this R1, and I'll stick with that R3. Yeah, I'm going to stick with that as R3 so they're not mismatched. There we go. So I'm kind of skipping out on a I2 or R2. That's okay. So V2 is going to be whoops. I'm changing my mind on my numbering. I don't want to mess y'all up. Let's call this, yeah, V2, so R2. And this V3, so R3. And then this will be V4, therefore R4. Just to be consistent so the numbers don't start looking weird. And so let me change these subscripts. So this will be V2, and this one will be V3. Okay, so now in terms of my current, going back to what I was trying to do in the first place, V2 then is I1. This is my current here, times my what I've labeled as R2. So just be consistent, pick away and run with it. And then plus my V3, I've labeled that as R3. What current is that? Well, I've labeled that as I2. So I2, R3. Okay, so we've done that one. Now, go ahead and do the 10 volt one on your own and come back and see if it matches what I'm going to do. Okay, so for this one, I'm going to say I'm coming out of the positive. So I'm going to make a loop going this way. Coming back. And so that says, again, I have this 10 volts. I'm going to lose some of that going across this resistor 3. And I'm going to lose the rest coming across resistor 4. So this is going to be 10 volts equals, let's see, I2 R3. And I've labeled that high to low. This is high to low. So I2 R3 plus, let's see, I3 R4. Okay, I'm going to call this 1 and this 2. So these two things right here, these are my loop rules. Loop rules. My junction rule is looking in terms of just adding my current. So I can look at this piece right here and say, so I2 is coming in and it's splitting into I1 plus I3. I can write that in any order. I mean, it's just mathematics, right? So what I always encourage people to do is look for the thing going into a junction, a current that you've already labeled, and what it's splitting up into. And so my 1 and my 3, they had better equal I2, otherwise I don't have conservation. So what I've done here is made a third equation. So number 3 is going to be I2 equals I1 plus I3. Now let's think about why we did this. Let's see. I don't know the current on I1. I don't know the current I3, and I don't know the current I2. Using the way we have done things, well, I can't solve for them the way we've already established because I have two power sources. So with two power sources, using my resistors in series and parallel isn't going to work for me. So that means I have 3 equations and 3 unknowns. So for however many equations you have, for however many unknowns you have to make that amount of equations in order to solve. So now let's take a look at how that looks once we start solving it. All right, when I look at this, one of the first things I think of is, well, I've already defined I2 in terms of I1 and I3. So if I want to solve this, the first thing I can do is make this substitution. So I'll have my 5 volts equals my I1 R2 plus my I1 plus my I3 times my R3. And then I'm going to simplify this a little bit. Then I have 5 volts equals I1 R2 plus I1 R3. Oops, don't drop your subscripts. Plus I3 R3. You're going to see why I'm doing this. And now I want to combine my unknowns. So reminder, I know what the resistance are on my resistors. I don't know what my currents are. So I have 2 I1, so I can simplify this down to 5V equals I1 times R2 plus R3. And then that's going to be plus my I3 R3. Cool. Might not feel like I've accomplished much, but what do I want? I need to eliminate either I1 or I3. And I can look at this one here. I have an I2 that I can write in terms of I1 and I3, which is going to be helpful because then I'll have 2 equations in terms of 2 unknowns, and they're going to be the same unknowns. So now I'm going to write my 10 volt. So let's call this 4, where I have 10 volts equals, let's see, which substitution am I making? Making the I2 into my, taking this one and putting it in there. How's that? So I1 plus I3 times R3 plus I3 times R4. And again, I'm going to simplify that and distribute so I can combine things. So I1 R3 plus I3 R3 plus I3 R4. Cool. And rewrite it again. This will be equation 5. It's going to be 10 volts equals, let's see, I1 R3 plus, and I'm going to factor out the I3. So I have just numbers here, R3 and R4. There we go. Now I can, let's see, what do I have? I have I1 and R3 and I1 and R2 plus R3, or I have I3, R3, and I3 in terms of those. So pick one, because what I'm going to do is multiply them both by, like, you can think of it as a common denominator. So I can subtract one equation from the other to get rid of one of my variables. So what I think I'm going to do is multiply equation 5. I'm going to multiply it by, let's see, if I get rid of, if I want to get rid of my I1, I'm going to have to multiply equation 5 by negative R2 plus R3. And I'm going to need to multiply equation 4, so that gets me an I1 times an R2 plus R3. Equation 4 needs to be now multiplied by an R3. I'll multiply both of those. So I'm going to make a new equation 6, just starting with this. Multiplying that by R3, I'm going to get R3, or so 5 R3 equals R3 times I1 R2 plus R3 plus I3 R3. There we go. Oops, oops, oops. R3 squared, right? Multiplying it through. And it didn't go. Oh, computer, don't do this to me. It did it to me. Did we lose anything? Just everything I just wrote, huh? Okay. Just gonna pick up where we left off. So 6 is multiplying it by R3. We're just going to do that again. So plus R2, R3, plus I3, multiplying by R3, so R3 squared. And equation 7, I'm multiplying it by a negative of my R2 plus my R3. So I have 10 times, or minus 10 times R2 plus R3 equals, I'm multiplying it through, I1 R3, and this is a minus, times R2 plus R3. You see what's going to happen when I add these two together? This statement and this statement now are identical, so that piece is going to cancel out. Plus I3, oops, minus, multiplied it by negative, minus, there we go. I3 times R3 plus R4 times R2 plus R3. Cool. I've written it out symbolically. Let's do ourselves a favor, because this is going to get gnarly with that, having to FOIL that out. Let's go ahead and figure out, whoops, wrong class, sorry. Let's write out our defined values. So R2 is 3 ohms. R3 is 5 ohms. And R4 is 7 ohms. Just going to kind of simplify it down here. And there's nothing wrong with doing that. What I would say, my suggestion to you is to resist putting values in for as long as you can, so it's a little more visually apparent what you can do to simplify things if you leave them in variable form as long as you possibly can. Now I think we've accomplished as much as we can with this. So I have negative 10, R2 plus R3, well that's 3 plus 5, so times 8, equals negative I1 times R3, which is 5. Let's see, R2 plus R3 is 8 times 5, so that's 40. Minus, so this was 8, just in case everybody's wondering where that's coming from. This is 8, and then R3 is 5. So 5 times 8 is 40. Minus I3, R3 plus R4, 7 plus 5 is 12. R2 plus R3 is 8. 88, 96. Okay, so we have that one. Now let's simplify down equation 7. So this, I'm sorry, equation 6. So this is 7 rewritten. And now 6 is 5 times R3, which is 5, equals negative, I'm sorry, starting to do 7, equals R3, which is 5, times R2 plus R3, 8, 40. Yeah, it should be the same. At first I was having a little bit of a panic attack. I1 times 40. Because those two quantities are going to cancel. That's my double check that I'm not making mistakes with my math. See, plus I3, and R3 is this 5. It's squared, so 25. All right, so now let's see what those things equal. Okay, so that tells me that I3, so the two negatives are going to cancel, so I'll get that I3 equals 55 divided by 71. Like 0.775 amps. All right, so we have one unknown. Now what I can do is come back to one of these. This is I3. Let me make a note. Equals 0.776 amps. Now let's look for one that has just I3 and somebody else. Let's see. I have here. Whoops. Yep, here. So I can solve for I2. Let's do that. I'm going to squeeze it in. Let's move this up a little. I'm going to squeeze it in over here. I have 10 volts equals I2 times R3, which is my 5 ohms. So 5 times I2 plus I3 is that 0.776 times R4, which is 7. And then let's just subtract that. So 10 minus that guy times 7 gives me 4.58 equals 5I2. So finally we can solve for I2 by dividing the 4.58 by 5. And I get I2 is 0.915 amps. Make that list here. 915 amps is I2. So now I'm looking for the easiest one to solve. Well, I have I3, I have I2. Let's solve for I1. So I1 then is going to equal I2 minus I3. I3, so this is I2 is 0.915 minus I3, 0.776. And I get that I1 is 0.141. I have solved the circuit. So let's take this back and look at our original circuit. Ooh, not delete, undo. Copy. Again, not chemistry. There we go. Let's just put this here. Okay. Actually, I want it on the circuit so I can actually see what we're doing. So I3, which one has the bigger amount of current? It's going to be I2. And that makes sense, right? So I'm going to have current coming out of the 10 volt. This direction that I chose here is not going to have any. It's very little. So I'm going to have current coming out of here and adding into here. So it makes sense that my I2 is the bigger, here's I2, is the bigger of them, because I have the two currents adding to one another. And then I3 is going to be the next biggest. Let's kind of see if we can't think that one through. What's our total resistance here? So it's telling me that I3, there's I3, is the path of least resistance. And that actually makes more sense because it's closer to the 10 volt source. So the 10 volt source can give out more current, so then it makes sense that it's going to get more current back. Because remember, conservation. All right, so the next video I'm going to do one more example and I'll leave a couple for you to do on your own with solutions. And then we'll be readdressing this on Wednesday. So be patient with yourself. The key here to the success is just being methodical. Don't lose your subscripts. Pay attention to what they are. Stay in your variables as long as you can, just because it's going to make it easier to spot things when the numbers aren't quite as neat and tidy as what we have here. Label your equations as you go. That's going to let you keep track of what you've used to get to what. Believe me, it gets easy to get lost. Do you have to do it the exact way I did it to solve? You might look at this and say, well, I could have made this substitution and this would have simplified faster. By all means, you can do that. Just a lesson learned in the past is that oftentimes in trying to make the math less gnarly, I spend more time looking for how to make it pretty than I do in just solving it. Because in the end of the day, most of our resistors, we know those. So we'll be able to simplify that down pretty nicely. All right, let's do one more.